Hi, this is Bill Freeman, and I'm delighted to present at the Diagram Image Retrieval and Analysis Workshop. So I have two pieces of work I want to show you. One's about generating and one's about interpreting line drawings across different variations in style. So there are two sort of case studies about that particular topic. Now, I got to warn you, both of these are from things I did a while ago. And so they are pre-revolutionary. They don't use CNNs. But, sorry, they're still worthwhile. Well, I think so. For one thing, if people have only remembered what happens in the past 8 years, these can be looked at as fresh ideas because they're from about 8 years ago. And also, I think these ideas are ready to be incorporated into modern interpretations. So let's just get started. So the first is about interpreting shapes, or given a line drawing or a rendering of a shape, how can you interpret it? And this builds on work that was done years ago. I just want to point this out. It's inspired by the Block's World image interpretation work of David Waltz and others. So just to remind you, in that work in the past, they had, your image was a Block's World image, just a line drawing of blocks. And the desired output is an interpretation of all the shapes and all the faces and orientations. If you assume that you have a clean drawing, then you can also assume that it's easy to transform the drawing into a set of line segments. And then the issue is just how do you interpret the line segments? And these are the sort of interpretations you want to make. You want to say what's caused by a shadow edge, a concave edge, convex, obscuring edge, occluding edge, or a crack. And so they developed these beautiful mechanisms of constraint propagation or compatibility rules, where, for example, let's look at this case where you have if you want to decide if a particular edge has a particular labeling, if it's convex, like looking down onto a roof of a house. And these are the different types of interpretations of the different sides, side 1 and side 2 of the edge. It can be illuminated directly from the light source, like this face is, or it can be a projected shadow region like this face is, self-shadowed region, self-shadowed like this face is, or a projected shadow, a cast shadow, like this edge is part of a projected shadow edge. And if you think these things through, you can come up with a set of compatibility rules saying that, yes, you're allowed to have, for example, this part of the block has two faces which are both directly illuminated by the light source, and it's a convex edge in between. So yes, that's allowed. But here, if you have a cast shadow under generic conditions, generic assumptions, unless there's a coincidental alignment of the cast shadow and another edge, you can't have a cast shadow edge that's exactly along a convex roof edge. And so this set of compatibilities is not allowed. So you can define what's compatible, what's not compatible, and then write down all the different constraint rules. This is just one rule, and come up with a labeling. So given an input image, just as of the intensities of these blocks, you could come up with a labeling of what each edge means and the shadows involved. I should mention this, this thread of research came to a dead end when it was hard to translate those heuristics from the Block's World clean images to real world images. But in some sense, the work that I'm going to show you is an attempt to actually do that, to go beyond. So we developed a method we called shape collage, which has a similar spirit to some of the work. The desired input was a rendering of a shape in any one of many different styles of rendering. It could be a line rendering of it. It could be a shaded rendering. It it could be a textured rendering. And from each of those different renderings, we wanted to be able to look at that image and compute what the three-dimensional shape was. So we're going beyond the blocks world in that we have more generally allowed shapes, but we didn't go too far beyond it in that we still had synthetically generated shapes. And this is joint work with Forrester Cole, Philip Pizzola, me, Fredo Durand, and Ted Adelson. And at the time, we were all at MIT. So, so how can we look at, so as a human, we can look at each of these three figures, and which could be parts of a diagram, I should say. And we can interpret them as a three-dimensional shape without much trouble, even though they look very different, and the presumed rules for going from that 2D image to a 3D shape must be very different in each case. And so how do we do it? How might we do it? Well, we don't know how we do it, but here's an algorithm we developed to address that task. We started with a synthetic world of normal maps and of shapes, these sort of lava lamp-like blobs. And the surface normals are indicated by color in this case. So these are the types of figures we randomly generated. And then we rendered each of these figures in a number of different rendering styles. So we have a line drawing style. These are actually not simply occluding edges, they're also so-called suggestive contours. Regions of curvature, minima or maxima, which are very close to being a contour if you move your head a little bit from the initial location. And shaded figures, so these are Lambertian shaded single light source. Shiny computer graphic single light source rendering, and then different styles of texture, just a texture map onto the surface, or texture map combined with shading, as shown here. So these are the 6 different rendering styles, and we want to develop an algorithm that will go from each of those styles and reconstruct a normal map or a shape from each one of those. So we're going to use a learning-based approach and an example-based approach. And basically, we're going to show the algorithm many different examples of such blobs and their renderings, and show what the answer is for each of those in the training set. And then from that, learn a method to go backwards, to go from these rendered shapes to the original 3D shape. We're not just doing it in total brute force. We're actually kind of thinking about the steps in a somewhat modular way. So rather than taking this all and putting it into a neural network, we used an example-based approach where we allowed ourselves to have many different patches of the image, where each one patch was assigned to a small area of the image and got to see what the rendered image looked like, and also what the true answer was, what the actual cause was in the world of making that rendered image. And then from these many examples, we want to infer our way back to go from a rendering to a shape. So here's how we progressed. We first, we wanted to break up the image into a number of discrete patches, and rather than do it in a sort of marching cubes kind of style, we wanted to pick them based on what were sort of the singular points in terms of scale and position. So we found key points in a mechanism similar to the SIFT features to find special locations or key points across scale and position. And so here's an example of the different key points that were found, and they're color coded by the scale according to the color and by their position. And then we would connect key points which were close to each other. So here's our network. Now the game is we want to look at each little key point place and decide what its possible interpretations are, and then make ourselves select from those many possible interpretations and make ourselves consistent with our neighbors. So again, it's in the same sort of spirit of aggregating local evidence and propagating local evidence across space. that same spirit as the Blocks World work of years ago. So step 3 then is to select a set of candidates that explain the local appearance of each of the key points. So here's an example. Here's a local patch. And here are 3 different patch candidates from our data set. Each of them looks approximately the same and can explain this local region, but each of them has very different interpretations. So, and again, this is the sort of generalization of the rules that we saw in the Waltz filtering. Here are the normals, which could create this line drawing. And here's a different set of normals, shape here, shape there, and then background there. Or this could be the background, and this could be a sharply turning kink, and that would also generate this same line drawing. So this configuration of lines just by itself is really quite ambiguous, and we want to come up with a diverse set of examples that capture that ambiguity. So now we have to resolve. So we do that for every key point, and now we have to resolve those ambiguities. And again, we do it in this compatibility framework. So between every neighboring set of key points, which they can be neighboring in position or neighboring in scale, we assign a compatibility between the different interpretations that are possible at each patch location. And so here we have the green patch is A, the red patch is B. And here are example interpretations for A. It could be that this part of this curve is figure, and yes, and this is background is ground. Or it could be that this part of the curve is figure and that part is ground. Or this could be actually not an occluding edge, but it could be a kink edge, and it could have this shape. Similarly for B. And then we can evaluate how compatible each interpretation of A is with each interpretation of B based on how much their shapes in the overlap region align with each other. And so you can make a measure of the disparity in the normal map for every possible candidate in A with every possible candidate in B. And here's a sort of visual depiction of that with an assessment. So we have a numerical assessment really, but here we're just showing intuitively what are the good assignments and what are the bad assignments. So these are incompatible. This with this is actually compatible, and so forth. And then we use an inference algorithm. In this case, we use loopy belief propagation to come up with a single best assignment of the interpretations for each patch, which are all consistent with each other, and to give a globally consistent interpretation. We used an algorithm that, well, so in principle, you could have perhaps global ambiguity as well, but we used an algorithm that would tend to pick a single optimal estimate. And so we maintained local ambiguities, but we didn't maintain a global ambiguity. And this was the stage that we called a shape collage. In other words, we represented the shape as a set of overlapping patches at different spatial scales, each with a shape and inclusion boundary interpretation locally. And this gives us this, here we're rendering that shape collage as an average of the different interpretations of each patch. And here's the average of the different rendered image interpretations for each patch as well. Then from here, we want to finally, this is a rather awkward representation of a shape, so we want to find a single curve, a single surface that covers all this, that best explains all these different patches. And so we make finally we make a fit a surface to those patches to find a single best interpretation. And then here for this example, here was the original shape that was created, the line drawing that we saw, and here's the estimated shape, which is quite close and has basically the occlusion properties correct, and perhaps could be forgiven for saying a line drawing of this would look like a line drawing of that. even though the surfaces are slightly different from each other. So just more details. We made 1,000 random shapes rendered from 2,000 different viewpoints and found key points, patches, etc. for each of those. We rendered each of those random shapes in the 6 different rendering styles. And then the answer that we recorded for the true shape that generated the renderings was the normals, the depth, and the occluding contours. These are more details. For many of these line renderings, you really have to be careful with the assignment of occlusions and foreground ownership, boundary ownership, and so forth. So I just want to take you through one example of that. Here's a rather complicated line drawing. And let's see. Here we're looking at ABC, A, B, C, yes. Okay, this is A, and this is B, and again, locally, B we could have, okay, here's patch A, and here's patch B. This is region of the image B. Sorry for that collision in letters. If we have 2 different patches that are over here, one here and one there, we could have an interpretation of patch A which says this is figure, this is background, and we could have one of patch B that says no, this is figure and this is background. And we, of course, want to be able to articulate that that's an incompatible one, and we can use both the shape but also the occlusion boundary the occlusion map to tell us that that's a bad and incompatible assignment of patch interpretations. And similarly for the good ones shown here. And the results, it worked really quite well. I don't think we compared it with how humans did, but that's rather hard to assess because sometimes humans find it hard to articulate exactly what is the 3D interpretation that they perceive when they look at something like this. But the algorithm is really quite explicit, and here's the original shape that generated it. Here's what the algorithm perceived to be the shape resulting from this image, and then also from this image. And you can see that its interpretations for the 2 are not exactly the same, but they're fairly close, and also as well fairly close to the original shape. So here's sort of a medley of results. On the top row, we have 3 test set shapes, not viewed by the training algorithm. And we have many different renderings of those. Here we have line drawing, we have shaded image, we have glossy shaded image, and sort of as a control, we have just the boundary. And there are some algorithms that can infer shape just from a boundary, which is not too much more information than, or it's a sort of analogous amount of information as you have here. But in this case, for this Brandeis control algorithm, we told the algorithm that the surface orientation was, these were occluding boundaries, and so it knew the orientation of the surface slope at the edge of that blackened region. It knew that the surface was normal to that slope. So, and this is a different algorithm not shown here of sort of inflation of generating one of the many possible shapes that would have this occluding boundary and the surface be perpendicular to the viewer at the boundaries there. So here we can see how the shapes compare when interpreting them from each of the 3 different rendering styles. So again, this could be different styles of rendering within a diagram. You could have a line drawing representation or a shaded representation or a glossy representation. And the reconstructions are really quite good. We felt they're fairly consistent with each other, as well as close to the original shape that generated those renderings. In this last column, we showed the 3 additional renderings that we had, the 3 different texture renderings. Here's a flat shading texture representation, and a soft shading and a glossy shading, diffuse shading and glossy shading. So it works pretty well, and we've generalized quite a bit from the blocks world rectilinear line segments of the previous domain. So at this point in a real talk, I would stop and answer questions, but we'll do that later in the CAPR workshop presentation. And now I'd like to go on to the second half of this on the analysis and rendering of lines in different styles, and that is how to render a line drawing in a number of different styles. So again, this is a learning-based method, but pre-neural networks learning. So the task is you want the user to be able to make a line drawing, and then you'd like them to be able to press a button and have it change the style of the lines used in the line drawing. Now you could do that in a mechanized way and just, for example, make them thicker or make them squiggly in some automated way. But we wanted to get the artist involved. And so instead we had asked an artist to draw a data set of lines in 3 different styles. Each of the line examples we asked the artist to say that it's basically the same content or the same line meaning, but to produce that content in 3 different drawing styles. So the 3 styles that we picked for this experiment, we called generic, jaggy, and brushy. So this first column is the generic style, jaggy, and brushy. So let's see, so the artist made 123 lines, and then we amplified that data set by replicating those lines over 6 different spatial scales and 4 different orientations, and then flipped left right. So that gave us a factor of 48 amplification for each of the 123, which gives 5,904 line elements in our data set, times 3 different styles. Here's just a kind of a detail point, but it'll come up later when we take linear combinations of these lines. What representation did we use within the computers to describe the lines? So we had, we digitized each line into a set of XY positions and had a stroke thickness associated with each XY position. And then to render them out, we fitted those with a cubic spline. We adaptively placed the control points for the cubic spline so that they would spend more time at regions of high curvature. And this helped us to get nice linear interpolations between our lines. If you had an example of 2 lines, A and B, and took their average, if you had even spacing of the control points of the splines, then you get a sort of mushy average of the 2. But if you did adaptive spacing and aggregated the cubic spline control points to have more higher density in the regions of higher curvature, then that tended to encourage the kink elements and lines to line up and give us a nicer average of the 2 lines here, being a line that looked somewhat halfway between them, but sharing the shape features of both lines. Okay, so here's the test image, also drawn by the artist, traced from a photograph of Einstein. So let's look at some of the ways that you might think to do the fitting and translation. So remember, we have this data set of 5,900 lines, examples, and you can go and for each one of the original lines of this drawing, you can just find the nearest neighbor in the data set that best captured this line. That gives you this rendering, this fitting rather, of the input drawing by the data set of artist-drawn lines. Now, once each of these is fitted with an artist-drawn line, we know how each one of these translates, according to the artist, into each of the other styles. So we can just take each of these lines and translate it into the style. So here we're translating from generic style to jaggy style. And we do that for each of the lines. And we get sort of an artist-drawn translation of this drawing into this translated version. So here's the point I want to make with this drawing. The translation works really quite well because it's already been vetted, if you will, by an artist. So each one of these lines was said to translate well into this line. But what doesn't work well is the fitting. So here is what the original line drawing looked like, but then when we fit it with our data set, we can only get a fit that looks this good. And so it sort of fits poor, the nearest neighbor algorithm fits poorly, but it translates well. You could also imagine a different algorithm. You could say, well, I want to improve my fitting. So instead of just taking the nearest neighbor of each input line into our data set, let's take the optimal linear combination of all our data set lines to best match each of the input lines. And that gives us this fitted input. So each one of these lines now is a linear combination of in principle, all of the training set lines. And so the fit is great. It's virtually indistinguishable from the original. But the translation, amusingly, is just terrible. So this fitted line might be some crazy linear combination of 100 times this line minus 432 times this other example line and so forth. And it fits fine, but when you take that same linear combination of all the translated versions of each of the lines involved in this line, then you get mush. So that's obviously not the right way to go. But interestingly, we can find a sort of compromise algorithm, which is really halfway in between those two algorithms I just described. And we call that the KNearest Neighbor algorithm, where when we do our fitting, we don't just take the first nearest neighbor, and we don't take all of them. We take somewhere in between. We take, say, the K closest neighbors of the input test line to find how to explain that line with our artist-drawn data set of lines. So here's different columns, the 2 nearest neighbor fit, the 4, the 6, the 10, the 20. And so you can see it gets really quite good. And by using 6 nearest neighbors, we can really explain the line quite well, even with our rather small, just almost 6,000 line set of examples that the artist drew. But what's nice then is when you take this small controlled set of nearest neighbors and translate and do the fitting and then translate the fitted version, it doesn't go crazy. And each one of the input lines is close enough to the original test image line that when you translate each one and then take the same linear combination of the result, you end up with something similar to what the artist might have done to translate this particular input line. So here's the fitting on this top row, and the translated versions are on the next 2 rows below. And while when you get up to 20 nearest neighbor lines, you start to get artifacts indeed. But if you restrict yourself to, say, just the first 6 nearest neighbor lines for your fitting, then you're safe to translate with that set. So again, just to make sure I've conveyed the algorithm, you take the input test image, which is here, and for each line, you want to explain it by some linear combination of your training lines that the artist drew. You find the nearest neighbors of it so that you're in a rather controlled space, and take the best linear combination of, say, the 6 nearest neighbors of 6 times the artist drew something that's very similar to that, and take a linear combination of them. And then if you do that, then you can translate, just plug in, replace each of the translated versions of the fitting ones to get a translation of the original test image. So, right, here's that story. Here's the input test image. Here's the fit to it with the 6 nearest neighbor algorithm. And now we translate. Here's the translated version of this fit and the translated version. This is from generic to jaggy and from generic to brushy. And here are other examples of the same story. So here's another tracing of an input image. This is this Picasso image. Again, the original as traced by the artist, and the 6 nearest neighbor fit, the translation of the fitted one, and the translation to the other style of the fitted one. And so again, it looks quite similar to the translations that the artist drew of each of the original training set lines. And one final example, the Sydney Opera House original fitted with the 6 nearest neighbor algorithm, translation of the fit, and translation to jaggy style, translation to brushy style. So that's it, these two methods to try to understand and generate line drawings such as you might find in diagrams or other drawings. First, the shape collage method, where we learned how to go from various different renderings of shapes, generic blobby shapes, and it was example-based, relied on a library of patches, and came up with the interpretation that was consistent with each of the, found the best interpretation for each of the local patches to come up with a global interpretation of the shape. And our approach allowed us to just plug in different rendering styles, so we could interpret line drawings, we could interpret rendered shaded shapes, we can interpret textured shapes. It's nicely general. And then, so that's for interpreting line drawings. And then also for rendering line drawings, we have, again, an example-based method to render line drawings in a number of different styles and to translate styles of these rendered images. Thanks very much. And I will look forward to answering questions and talking about these issues online.